Sometime in the 1970s, a super rocket, taller than a 20-story building, will be blasted into an orbit of the Earth from somewhere in the United States of America. It will be manned by astronauts who will have been trained for years for this mission. When its boosters drop away, burn up, and fall harmlessly to Earth, the main rocket will be guided by these men to an important rendezvous. They will stabilize their craft in a parking orbit around the Earth, and after precision checks of the actual orbit and an inspection of the space vehicle, space travelers will sit back and wait for a highly critical moment, a precise point in time and space when their powerful engine will snatch them from the pull of Earth's gravity and hurl them along their way. And at that moment, man's age-old dream of touching a star will start to become a reality. For this will be a manned mission to a celestial body. The engine that will make possible such a far outreach into the heavens will derive its great energy and efficiency from the power of the tiniest bit of matter, the nucleus of the atom. Such an engine is now being designed and developed, and this is the story of that engine. In another 5 or 10 years, man will be doing just that, traveling into outer space, to the moon, to the planets. 20 years ago, the scene you're about to see belonged only in the notebook of the science fiction writer, perhaps under the heading Remote Possibility. And then, in 1945, the awesome power of the atom's nucleus was revealed for all the world to see. And after that, nothing seems impossible anymore. This is Kiwi A, a nuclear reactor. You are viewing the first major experiment in Project Rover, the program to develop a nuclear rocket engine. This device and others like it were named Kiwi after the flightless New Zealand bird. They were so called because they were to be tested in this unflyable but most convenient nozzle-up position. The date of the historic event you are now witnessing is July 1st, 1959. This test, and those that followed, established beyond all doubt the feasibility of applying nuclear power to space propulsion. Project Rover began as a study in 1955, originally a Joint Atomic Energy Commission Air Force program. It is now sponsored jointly by the Atomic Energy Commission and the National Aeronautics and Space Administration, and is administered by an organization established by the two sponsors, the Space Nuclear Propulsion Office. Important research and developmental activities have been handled from the start by the Los Alamos Scientific Laboratory of the University of California. What is a nuclear rocket and how does it operate? Externally, it looks like any other rocket, and it operates on the same reaction propulsion principles. That is, a working fluid or gas under pressure is heated to a very high temperature, which causes it to expand rapidly and rush out a nozzle at high velocity, thus providing the thrust which sends the vehicle in the opposite direction. The speed of the individual particles at the exhaust end of the nozzle governs the speed of the rocket. As their speed increases, so the specific thrust of the rocket increases. A nuclear rocket differs in only one, but most vital respect, from a chemical rocket. The chemical rocket heats propellant by combustion, while the nuclear rocket heats it by fission energy. Combination of fuel and oxidizer become the exhaust products of the chemical systems, while the nuclear rocket may select its exhaust gas and picks hydrogen, the lightest of known elements, and much lighter than the typical chemical exhaust products. These can be more than 4 times heavier than the nuclear product. Because the push of a rocket engine comes from the speed of the propellant as it is ejected, it is more efficient to have a lower molecular weight, which gives a higher speed at a given temperature. For a far-out mission, like a landing on the planet Mars, a nuclear system has an advantage over a chemical system. because the nuclear system can get more push from the same propellant, or the same push from less propellant. That is to say, more power per pound of propellant consumed. Call it better mileage. Starting from an Earth orbit, such a mission would require a chemical system weighing 9,100,000 pounds, but a nuclear system weighing only 935,000 pounds. Thus, the nuclear system has clear weight advantage over the chemical system. The heartbeat of the atomic rocket is the energy which holds the atom's nucleus together. In uranium-235, this energy can be released by a process known as fission, a division which takes place when a neutron, which is an electrically uncharged particle hundreds of times smaller than the uranium nucleus, is absorbed by that nucleus. Here's how it works. A neutron strikes an atom's nucleus. It divides, or fissions, and liberates a great deal of energy in the form of heat. If it stopped here, we would have very little, if anything, going for us. But the fact is, it also releases other neutrons, which in turn are freed to continue the fission process, and a chain reaction will result if there are enough other uranium atoms around. Once again, a neutron strikes an atom's nucleus. It divides and liberates a great deal of energy, also releasing other neutrons, which thereby sets up a chain reaction. Now, how do you take advantage of all this energy? First, you need an atom that fissions easily. Uranium-235 is by far the most practical element for this purpose. You need quite a bit of it, and in the proper geometry, to start and maintain a chain reaction. Since slow-moving neutrons are better at causing fission than fast neutrons, you need a moderating material, such as carbon, to slow down the neutrons. Now, you need to control this activity, and one way is quite obvious. You simply withdraw atoms from the area and return them. Another means of control is to manipulate a neutron-absorbing material, such as cadmium. If you add a reflector material, such as graphite, you can bounce escaping neutrons back into the active area and greatly increase activity. Now, to take advantage of the tremendous heat generated by this fission process, you force a propellant gas or fluid through the area. As it absorbs heat, it expands, exerting thrust as it is forced out a nozzle. That's how Project Rover reactors should work. Theory is one thing, but the translation of ideas into design concepts and then into the final hardware stage is a long and difficult road. But it is a road that Project Rover has been traveling rather successfully since 1955. At that time, not even the problems that the project was facing were well known. Basically, Kiwi reactors have been the same from the start. Essentially, each has a core of fissionable material through which the hydrogen propellant can flow, absorbing heat as it goes. The liquid hydrogen enters at the nozzle, flows down the shell, absorbs heat, and is ejected from the nozzle, thus producing thrust. While this appears to be a very simple plan, there have been some formidable problems to be solved. For example, the use of hydrogen with its low molecular weight gives the nuclear rocket a big advantage over the chemical rocket. But its flow through the core complicates the rate of power generation, since hydrogen has a marked effect on neutron behavior. Another problem, the core is a tremendous heat source, which can actually melt the reactor. So the liquid hydrogen must serve as a coolant, as well as a propellant. Fuel elements must not only be able to withstand high temperature, but rapid temperature change, as well as the erosive and corrosive effects of moving hydrogen. These are just a few of the problems. A good many others crop up in the design stage when some very restrictive factors must be taken into consideration. A Project Rover reactor must be housed in a small package capable of high mobility. It must be able to run at very high temperatures. It must be able to start coal and come to full power very rapidly. It must be capable of restart, and all the while generating enough power to illuminate the entire city of Washington, D.C. Though administered by the University of California, the Los Alamos Scientific Laboratory is not situated in that state. It is located in northern New Mexico, high on the eastern shoulder of the Jemez Mountain. It is here that reactor concepts for the Rover program come into being. Once the general approach for a new reactor has been adopted, many wheels are set in motion. Mathematical concepts, core configurations are programmed on the laboratory's digital computers. By the use of these high-speed machines, a great variety of reactor designs can be studied. An analog computer is used to simulate actual reactor run conditions. To evaluate nuclear characteristics of a variety of reactor materials, a critical facility called the honeycomb assembly is used. It permits studies of neutron flux distribution for various fuel loadings and geometries. The core configuration to be studied is simply loaded into the honeycomb structure and the two halves slowly brought together. Remotely inserted rods control criticality. Once the basic characteristics of the new reactor are known, the reactor design staff at Los Alamos starts its wheels turning. All of the general information gathered to this point must dovetail together for the fabrication process. In order to give designers a better understanding of the physical properties of core materials at high temperatures, the laboratory maintains a test facility where specimens can be subjected to temperatures in excess of 4,500 degrees Fahrenheit. From powdered constituents, most of the uranium-loaded fuel elements that form the core of Kiwi reactors were fabricated in the laboratory. Early in the Rover program, uranium-235 was the obvious choice as the fuel material, but pure metallic uranium has a much lower melting point than temperatures needed in the nuclear rocket. Therefore, it had to be used as a refractory compound and be encased in a matrix of high temperature resistance. Graphite, which melts above 3,500 degrees centigrade, the highest melting point of any of the elements, was the choice. Graphite and uranium mix is blended in the proper proportions, then put through a grinder and compacted to ensure even mixing. Special facilities and procedures are necessary to prevent contamination of personnel and equipment by the radioactive uranium powder. While fuel elements are being fabricated at Los Alamos, the pressure vessel and most other non-nuclear components are being constructed by contractors outside the laboratory. Most hardware and piping are made of aluminum because of its high strength-to-weight ratio, ease of fabrication, and short radioactive half-life. Other components are being manufactured elsewhere, like the reactor nozzles, which have been made on the Pacific coast for shipment to the Nuclear Rocket Development Station, the test site, in Nevada. Test operations on Kiwi reactors begin at Los Alamos. Each reactor is assembled in the Los Alamos Critical Assemblies Laboratory and checked out at very low power. Once criticality calculations are confirmed, the reactor is taken apart and shipped to Nevada for full-scale testing. In the southern Nevada desert, at a place called Jackass Flats, some 90 miles north of Las Vegas, is the test area, the Nuclear Rocket Development Station. This consists of three basic operating areas: the control point, the maintenance assembly and disassembly building, MAD or MAD building, and the test cell tank farm complex. The MAD building is used for assembly of the reactors to be tested and for remote control disassembly and post-mortem analyses of the reactors after the test runs. Once assembled, reactors are transported to the test cell by battery-powered locomotives and are literally plugged into the test cell by the use of a special connector on the front of the test car. This connector contains all control and instrumentation lines and mates with a matching unit on the face of the test cell. The piping which furnishes the propellant supply is connected in a similar manner, a system allowing remote control of both a disconnect mechanism and transport of the reactor back to the MAD building after the test. Storage facilities for the hydrogen propellant and nitrogen gas for purging the reactor before and after the test are located near the test cell. A complex network of valves, all remotely actuated from the control point 2 miles away, controls the flow of gas and liquid to the reactor. The vast array of data acquisition and control equipment is located at the control point. Emphasis is placed on fast automatic data handling using large-scale digital computers in conjunction with tape-recorded data. Facilities are provided for making nearly 1,000 simultaneous measurements of such important items as temperature, pressure, and power. This information is automatically recorded on strip charts as the test progresses. In addition, measuring devices on the reactor generate small electrical signals which are transmitted to tapes in the control point. The tapes are available immediately after the test for translation by digital computing machines. With all systems getting a final checkout, the test reactor is just about ready for its big moment. Just before a test, the area is cleared of personnel, the control cylinder actuators unlocked, and the entire system put in remote control condition. Before the reactor is brought to a critical state, each operator responsible for a particular reactor function carefully checks his control against the checklist and reports his ready status to the chief test operator. Only when it is established that all systems are operating properly is the reactor brought to a low power level. It is then flushed with nitrogen gas and all systems checked once again before switching to hydrogen flow. Flow of helium and later of nitrogen reduces the reactor core temperatures smoothly to a safe level. With the reactor test completed, a great deal of work remains to be done. The reactor is taken apart in the MAD building for a visual inspection. Some of the parts will be examined more closely later, and many will be returned to Los Alamos for radiographic and X-ray examination. All of the information derived from the test and post-mortem examinations will be coded and fed into computers, and the results will be incorporated into future reactor designs. The Kiwi Reactor Development Program is the first phase of Project Rover. An industrial team, Aerojet General Corporation, and Westinghouse Electric Company takes over the second phase, known as NERVA, Nuclear Engine Reactor for Vehicle Application. NERVA is followed by RIFT, Reactor In-Flight Testing, handled by an industrial contractor, Lockheed Aircraft Corporation. In the meantime, while providing technical assistance to the NERVA contractors, Los Alamos Scientific Laboratory is working on the development of higher-powered reactors and advanced concepts.